Welcome to the unit of Hadoop Fundamentals on Hadoop Architecture. I will begin with a terminology review. Then I will cover the two major components of Hadoop, the distributed file system component and the MapReduce component, with an emphasis on a distributed file system called the Hadoop Distributed File System, or HDFS. We will see what types of nodes can exist in a Hadoop cluster, and I will explain an important feature of Hadoop called rack awareness, or network topology awareness. I will end with an example of how a file is written to HDFS to illustrate replication. Before we explain Hadoop components and architecture, let's review some of the terms that are used in this discussion. A node is simply a computer, typically a non-enterprise commodity hardware for nodes that contain data. So in this example, we have node 1. Then we can add more nodes, such as node 2, node 3, and so on. This would be called a rack. A rack is a collection of 30 or 40 nodes that are physically stored close together and are all connected to the same network switch. Network bandwidth between any two nodes in this rack is greater than the bandwidth between two nodes on different racks. You will see later how Hadoop takes advantage of this fact. A Hadoop cluster, or just cluster from now on, is a collection of racks. Let us now examine Hadoop's architecture. Hadoop has two major components: the distributed file system component, the main example of which is the Hadoop distributed file system, though other file systems are supported, and the MapReduce component, which is a framework for performing calculations on the data in a distributed file system. This unit will cover the Hadoop distributed file system, and MapReduce will be covered separately. We will now examine the most important distributed file system in Hadoop, HDFS. HDFS runs on top of the existing file systems on each node in a Hadoop cluster. It is designed for very specific data access patterns. Hadoop works best with very large files. The larger the file, the less time Hadoop spends seeking for the next data location on disk, and the more time Hadoop runs at the limit of the bandwidth of your disks. Seeks are generally expensive operations that are useful when you only need to analyze a small subset of your dataset. Since Hadoop is designed to run over your entire dataset, it is best to minimize seeks by using large files. Hadoop is designed for streaming or sequential data access rather than random access. Sequential data access means fewer seeks, since Hadoop only seeks to the beginning of each block and begins reading sequentially from there. Hadoop uses blocks to store a file or parts of a file. This is shown in the figure. Let us now examine file blocks in more detail. First of all, blocks are large. They default to 64 megabytes each, and most systems run with block sizes of 128 megabytes or larger. A Hadoop block is a file in the underlying file system. Since the underlying file system stores files as blocks, one Hadoop block may consist of many blocks in the underlying file system, as shown in the figure. Blocks have several advantages. First, they are fixed in size. This makes it easy to calculate how many fit on a disk. Second, by being made up of blocks that can be spread over multiple nodes, a file can be larger than any single disk in the cluster. HDFS blocks also don't waste space. If a file is not an even multiple of the block size, the block containing the remainder does not occupy the space of an entire block. As shown in the figure, a 420 megabyte file with a 128 megabyte block size consumes 4 blocks, but the fourth block does not consume a full 128 megabytes. Finally, blocks fit well with replication, which allows HDFS to be fault tolerant and available on commodity hardware. As shown in the figure, each block is replicated to multiple nodes. For example, block 1 is stored on node 1 and node 2. This allows for node failure without data loss. If node 1 crashes, node 2 still runs and has block 1's data. In this example, we are only replicating data across 2 nodes, but you can set replication to be across many more nodes by changing Hadoop's configuration or even setting the replication factor for each individual file. The second major component of Hadoop, described in detail in another lecture, is the MapReduce component. HDFS was based on a paper Google published about their Google file system. Hadoop's MapReduce is inspired by a paper Google published on their MapReduce technology. A MapReduce program consists of two types of transformations that can be applied to data any number of times: a map transformation and a reduce transformation. A MapReduce job is an executing MapReduce program that is divided into map tasks that run in parallel with each other and reduce tasks that run in parallel with each other as well. Let us examine the main types of nodes in Hadoop. They are classified as HDFS or MapReduce nodes. For HDFS nodes, we have the name node and the data nodes. For MapReduce nodes, we have the job tracker and the task tracker nodes. Each of these is discussed in more detail later in this presentation. There are other HDFS nodes, such as the secondary name node, checkpoint node, backup node, that are not discussed in this course. This diagram shows some of the communication paths between the different types of nodes on the system. A client is shown as communicating with the job tracker. It can also communicate with the name node and with any data node. There is only one name node in the cluster. While the data that makes up a file is stored in blocks at the data nodes, the metadata for a file is stored at the name node. The name node is also responsible for the file system namespace. To compensate for the fact that there is only one name node, one should configure the name node to write a copy of its state information to multiple locations, such as a local disk and an NFS mount. If there is one node in the cluster to spend money on the best enterprise hardware for maximum reliability, it is the name node. The name node should also have as much RAM as possible because it keeps the entire file system metadata in memory. A typical HDFS cluster has many data nodes. They store the blocks of data, and when a client requests a file, it finds out from the name node which data nodes store the blocks that make up that file, and the client directly reads the blocks from the individual data nodes. Each data node also reports to the name node periodically with the list of blocks it stores. Data nodes do not require expensive enterprise hardware or replication at the hardware layer. The data nodes are designed to run on commodity hardware, and replication is provided at the software layer. A job tracker node manages MapReduce jobs. There is only one of these in the cluster. It receives jobs submitted by clients. It schedules the map tasks and reduce tasks on the appropriate task trackers in a rack-aware manner and monitors for any failing tasks that need to be rescheduled on a different task tracker. To achieve the parallelism for your map and reduce tasks, there are many task trackers in a Hadoop cluster. Each task tracker spawns Java virtual machines to run your map and reduce task. This lesson continues in the next video.